this
You're the
computer.
host.
We are recording, I'm pretty sure.
Excellent.
Wonderful. Thank you for the reminder. Slideshow. Okay, can everyone see this?
I can see it. You are good.
Okay, we're just going to assume everyone else can see it. Welcome, welcome, welcome. It is week 8 of Sunday Reviews. Today we are talking about trees and binary search trees and all that good stuff. In comparison to recursion, it shouldn't be as difficult. I think, well, for me personally, it was more intuitive than like other things like recursion. That took me a while. But trees do use a lot of recursion. So let's get started. Any questions before we start? Anything you'd like us to focus on? No? Okay. Well, we're just gonna start then. Trees. What are trees? Oh, here it is. Okay, so it's like trees versus like linked lists. So trees are kind of like the more advanced version of linked list. As you can see in linked list, you only point from one element to another. And even if you have a doubly linked list, you're only pointing to a single element. Like your pointers are only pointing to like one or the other. While trees, it's like a linked list combined, where like a parent kind of be pointing to several elements. So you can see like each of these parents. Oh, let me get a little pointer out. You can see how there's so many like pointing things, so many arrows from one node, versus in linked list, one arrow can only go out from one node. So this one is left to only one arrow, and this one has like 3 arrows. Yes. Okay, here is kind of like your cheat sheet for trees and the terminology. So here we have the root, which is like the topmost node of your tree. You will also have your key, which is whatever's inside. Your edge is kind of like the connecting thing, the connecting side of P and R. Leaf nodes, yes. Leaf nodes are like anything like at the very bottom. So they're basically childless. These leaf nodes are basically childless. They're not apparent to anyone. And then these are just nodes. Just each, like from P to E to G, H, I, these are all nodes, like individually, they're nodes. You can also have siblings, we're working like a family tree here. Yes, an important thing to note is that a tree is basically made up of subtrees. So here, this is a subtree. You can take like LQ, QALB as a subtree. You can take RCD as a subtree. And what this basically means is that fundamentally trees can be traversed, can be like gone through recursively, since you can basically break up your whole problem into like mini problems, and they're all solved the same. For example, if you want to look like through all the children of this, then you can first see the full thing, and then you can break it up into these two smaller trees. And similarly, you can break it into this subtree, into this subtree, into this subtree. And as you can see, like slowly, you're making like mini trees until you can actually get to the edge case of hitting a leaf node. Yes. Yes. Binary trees. Okay. What we have at the right here, this is not a binary tree. So a binary tree is just basically each node can have at most 2 children, kind of like a linked list can have at most one child. A binary tree is just like a step up, which can have at most 2 children. Note that just a normal tree can have like basically infinite number of children. It would kind of be a terrible tree if it had infinite number of children, but it would still be a tree. Here we have some terminology. So we have a root node, the topmost node. Left node is the left child. Right node is the right child. And like a branch is just like a subsection of the tree. So just this section, you know what I mean? This is terminology, and luckily for everyone, they use pretty intuitive names based on trees. It didn't try to come up with a fancy name, which sometimes happens in science. Okay. Oh, any
Yep.
questions on trees or such? No? Okay, we're going for binary search trees.
Yep. And
Do you
I
want to
can
share
go
your
ahead.
screen or
Yeah, so that I can. Oh, you
there you go.
disabled participant screen sharing and you didn't make me a co-host. That's
There you
okay.
go. There you go. I got you. I got you. I think I
You
just
got me?
changed it.
All right.
I got you. Don't worry.
Awesome. We've got this. You can go ahead and go to the next slide. This
Oh wait.
one's
Oh I meant that you can share your screen now.
Oh, I can now. Okay, there we go.
There.
Ha ha ha.
Wonderful, wonderful.
Let me just hide slideshow.
You have
Can
such
you
a
see
big
it?
mouse.
It's because I'm on my big monitor, so it's
Um,
displaying weirdly through the screen share.
oh, interesting.
Yeah, I found that one out on my own. Very fun time. So just real quick, Sophia just went over this stuff, so you're gonna just be real quick on this slide. So root, the node at the very top where the rest of the tree originates from. You got the leaf, which is a node with no children. The parent, which is the node that the reference node comes from. So like if you were considering node 3, the one with key 3, you would be considering the parent node as node 2. And then child is the opposite. And then when I reference traversing through a tree, it just means going down through the tree. Not so I believe you've already gone through like in order traversal, pre-order traversal, and post-order traversal. Generally for this, for binary search trees, you're going to be using in order traversal. So that's going to be what I'm referencing the most for that kind of traversal. Obviously, as you are going down through the tree, you're going to be using binary search type, which is going to be just going straight down. So searching, you're traversing down the tree. So you determine which child to move to based on whether the key is larger or smaller than the desired key. The key, obviously, the key being the element of the node. So I put a quick little piece of code that you can reference there. So you've got, say you start at 5. I'll use my comically large mouse. So you start at your root node, so 5, and if you're looking for, say, let's say we're looking for 21, you would know that 21 is larger than 5, and so you would go down to this subtree, right? So breaking it down into that smaller tree and calling the function recursively on that subtree. So then in that call to the function, the root would be 17. And you would say, oh, 21 is still larger than 17. Then you would break it down here and you would know that in this subtree, the root node is 21, which is what you were looking for, and you have found the correct node. And then inserting, so you're going to always put in the inserted node as a leaf. So you're going to be searching through using that search method I just went over, and then you'll be determining based on where you end up searching for that node at the very bottom, where that leaf is going to go. So I have a couple examples here to our the example on the right. So you see that we're going to insert 95. So we're traversing through, seeing the same way we did that search, and we go over to 75, like 95 is still larger than 75. We go to 85, make that the root of this subtree. There's nothing left, but we know that 95 is greater than 85, so we're going to make it that leaf, that kind of right child for all that that matters when there's only one child, to the be where that inserted node is. So it will be the right child of 85, as it is larger than 85, but there is nothing beyond 85. And then on the left, the bottom example, we see one where it's not the largest item, so we're inserting 26, and you see that 25 is less than 26, 29 is greater than 26, so we go down to the left child. We have 28, which is also larger than 26, but there's nothing below 20. There are no children of 28, so we stick it as the left child of 28. Okay. And then erasing is fairly simple. I have two quick little visual examples. So there's three different types of erasing. There's where the one you're erasing is just a leaf, and so then you would just delete the node and there are no further actions you need to take. There's the node having one child, so you would just replace that node with the child node, so it would just move upwards. And then you have the node that you are deleting having two children, so you need to determine which child is the successor node and replace the node with that child. Generally, that's going to be the left child, as it is the smaller one, but still larger. But there can always be different situations, but generally you're going to find yourself with the left child being the successor node. So I have two little visual examples over here. So the top one is just, we're deleting 50, so we're deleting the root. And in this example, in order to keep a more balanced tree, the successor node is actually the right child, to keep a more balanced tree. Otherwise, it would no longer be really a tree. So that's what I mean when there will be situations where you want to use that right node, but that right child. But generally it will be your left child in most situations. And then in the bottom, this one is just picking not the root node, but it is one with two children. So we're getting rid of 6 here. And so we have determined that the node to swap is actually not a direct child. It's the leaf node. It is the left child of 8, as opposed, because it is the one that is closest to it in number. And so you end up swapping the two nodes and then deleting that child node that was now the 6th node. That's a little unintuitive for some. It's the more you look at it and the more you look at different examples, the more intuitive it becomes, but it is not initially that easy to understand. But the most important bit is that you are finding your successor node, you are swapping the successor node and the node that you would like to delete, and then you are deleting that bottom node. So yeah, it's so are there any questions? If not, I'll throw it back to you, Sophia. You are muted if you have not realized.
Okay, thank you. Yes, tree traversal is the next part. Yeah. Okay. Oh, there you go. Okay, so there's like 3 different kinds of tree traversals that we've talked about. There's pre-order, post-order, and pre-order, in-order, and post-order. So let's just go over them one at a time. So pre-order, that's, as you can see, actually I'll have them all open. Okay, let's focus on this pre-order. Notice how when we call things recursively, the first thing we're gonna do is we're gonna actually like do, quote unquote, do what we want with our node. So in this case, we're gonna run our node command first, and then we're gonna call 2 recursive functions, one to the left and one to the right. This differs, for example, from in order, where you have your print statement in the middle, and this differs from in post order, where it has your print statement last. So let's go and kind of walk through exactly what pre-order and post-order and how they actually work, because this is very important to, like, these are really good mental exercises to do in order to understand recursion and how it actually works out. So if you still are unsure on how recursion works, this is a great exercise for you to go over. So let's go over it together. Wow. Okay, so first we're gonna start at this node 8, right? We're gonna pass in. Let's say we pass in node 8 here and here. Okay, so our node is not null pointer, and so we're gonna print out our node. So we're gonna print out 8. Next, it's gonna tell us, okay, look to your left. So we're gonna go here. So we're passing in node 3 now. Similarly, we're gonna look. Notice how we're in a subtree. And because this 3 is also a tree, we can treat it exactly the same. This is why recursion works with trees. Because this 8 and this 3 are both acting the exact same way. They have the same properties. So we're at 3, right? Next, we're gonna print out 3 because it tells us, and now it's telling us, oh, print left. So we're gonna go down. We're in the printing, now we're in the pre-order print node 1 function. And now we're here, we print 1, and we're gonna go to the left again. Boom. Notice how our node is now a null pointer. We're like down here. So what happens if it's a null pointer? Nothing, we return, we're done. So we basically skip all this, and now we've popped back. Now we're at 1 again. We have just completed this node left function, and now we're gonna go to this node right function. So we're gonna go to node right. Notice how it's also a null pointer. So once more, we're done with that one. We pop back. We have finished our node 1 function now. We have pre-order printed left and we have pre-order printed right, and both of them have popped back. So now it's time for this one to be done. So we pop back to 3. Notice how now we're at 3, but in our 3, we haven't done the pre-order print node right. We've done the left one, but we're not done. We have to go to the right. So we're at 3 now. And now we get to go, we're going to go to our 6. And now we're pre-ordering printing. We're going to look left. Oh, we print out 6. My bad. We print out 6. And now we're going to go to our left. We print out 4. We're going to check left and right. There's nothing there. So we're going to pop back to 6. And so on and so forth. So does everyone kind of understand what's going on here? Okay, good. So I'm just going to finish this exercise a bit quicker. So we're at 6. We print out 7, and we look left and right. There's nothing there. So we pop back to 6. We're done with 6. We've looked both left and right. Pop back to 3. We've done with 3. We've looked left and right. Pop back to 8. We haven't looked at the right yet. So we're going to go here to our 10, print out 10. Then to our 14, print out 14. Oh, sorry. We're going to 10. Look at our left. Notice there's nothing. Pop back. Then go to 14. And then go to 13. And then we look at both sides. It's null pointer. So we pop back. And look to the right. And notice how it's a null pointer. So that's kind of how we got this set of numbers. I'm going to do in order a bit quicker as well. Hopefully we now understand how recursion kind of works. And if not, please feel free to like speak up. I mean, we're doing this for you guys. So I mean, kind of useless if you don't understand and you don't say anything. Okay. So in order print, this is our 8. We're going to look to our left first. Okay. We're going to look left. And then we're going to look left again to our 1. And then we're going to go look left. There's nothing there, so we pop back. And now we go to our next command. Notice our next command is print out the node. So we print out 1. And now we're going to look to our right. There's nothing there. We pop back. We pop back. We're done with the left with our 3. So now we're going to print out 3. This is kind of a lot, guys. I understand. So we print out 3 now, and then we're going to go right. Okay, so now we're going to... What in order print basically means is just go left as far as possible. And if there's nothing more at the left, pop back, print it out until you can go right. So with that in mind, we're going to go 6. There's still something on the left. So we're going to go to 4. Then we print out 4, go back, go 6, print out 6, then 7. There's nothing to the left or right. Print out 7. And then we basically like really pop back. We're done with the left side. So we get to print out 8. And then we go to 10. And then there's nothing here on the left. So we print 10. And then we go to 14. And then we go to 13. And then we print that out. Wow, there's so much, guys. I'm sorry. Okay, now post order. We're going to do the exact same thing, but this time what we're basically saying is go all the way to the left and then all the way to the right. And finally, after all that, you get to print out your node. So basically we go all the way to the left, which goes to 1. And we're going to look right and there's nothing there. So we get to print that one out. We're back to 3, but then we have to do the same thing again. We go all the way to our left. So that hits us to our 4. And then we go back and then we have to go all the way to our right and then we hit 7. And finally we can go back to 6 and then 3. And then we have to still go for this 8. We still have to go all the way to the right and left. So we go all the way here to the bottom, 13, 14, 10, and 8. Okay, that was kind of a lot. I did this for the benefit of y'all to kind of understand how recursion works and the basics, but there is an easier way, and it's called the Euler-Tour technique. I said it was easier, but some people find it harder. I really didn't understand it until this semester. I didn't really care about it, but now that I understand, I'm like, wow, I wish I'd known this when I took this class. So now I'm passing on the knowledge to you. So basically, a Euler-Tour technique, it's ways to quickly do pre-order, in-order, and post-order. And what you're going to do is that at each node, you're going to imagine there's like a little dot to the left. And when you visit that dot, that's when you print out your, print out the value. Notice how there's like an arrow and it kind of just like surrounds the whole thing. It's like a little fancy border. For pre-order, you're going to imagine a dot to the left. In order, you're going to imagine a dot to the bottom. And post-order, you're going to imagine a dot to the right. So let's do pre-order. You're going to see how this is so much faster. Okay, follow my little pointer here. Okay, so pre-order. We're going to start at here. Oh, what did I do? Okay, yes. Here. We're going to go to pre-order. So we start here. Oh, we hit this 8, so we print out 8. Then we hit 3. Then we hit 1. Then we hit 6, 4, 7. Go all the way back here. Hit 10, 14, 13. And that indeed is our answer. So let's go over this again. We hit 8, 3, 1, 6, 4, 7, 10, 14, 13. As you can see, this is way faster than the other way. Okay, let's do the in order. Actually, you know, we're gonna try to go a bit. I'm gonna test to see if you guys are there. because sometimes they wonder if you are. So using this Euler technique, can people put in the chat what they think the answer is? Dun, dun, dun. Are we having participation? So yeah, so it's going to be the same thing. You're just going to like basically follow this like line. And whenever you hit these dots, you'll print out the node. So go ahead and do that. This will be a great test. Dun, 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 dun. I don't know how much time to give y'all.
I'd say just a little bit.
We'll give you guys like a minute or two.
Yeah.
There you go. Just remember, whenever you hit these dots, you just print it out. Dun, dun. Okay, is anyone like working on it? If not, I'm just gonna say the answer for the sake of the recording. But if not, I totally get it though. I did this for my Sunday reviews. I would just put it on and then, oh, Oma, thank you. Let's see, 1, 3, 4, 6, 7, 8, 10. Yes, the right person. No, you're good. You're good. Oh, look at this. Learning is being done. 1, 3, 4, 6, 4, 7, 8, 10, 13, 14.
Yep.
Okay, I can see why the left part would be confusing because you're unsure whether to put the 10 like dot on the right or on the left. We can go through that. Okay, wonderful. So in order, we're gonna go down. Whee! We hit this 1, and so we're gonna print out 1. Then we hit this 3, then we hit this 4, then we hit this 6, 7, 8, we hit 10, 13, and 14. Okay, so one reason that this right part is confusing, that it's a very good point to bring up, is that when you're doing in order, it has to be between the left and the right pointer. So the reason on this 10 that you have the dot here, right here on quote unquote the left side versus the right side, is because it has to be to the left of this right pointer. Similarly, the reason this 14 is on the right side versus on the left side is because it has to be on the right side of the left pointer. So you can just imagine if this 10 had also a little like left pointer to null pointer, and this 14 the right to the null pointer on 14, then we want it right smack in the middle. That is where you would put this node. So as you're traversing this, you're just gonna make sure to put your dot in between the left and right. And if nothing's drawn, just imagine there was one drawn, and then that will give you the answer. Does that make sense? Okay. I'm gonna hope that made sense to Oma. I hope I'm not butchering your name. I'm very sorry if I am. Okay. We're gonna assume that cleared things up for you. If not, I'm sorry. Oh. Oh. So yes, Oma. Yes, no? I'm sorry. It's okay. We're gonna move on. Oh, nice. Okay. Does everything make sense? Like, did that clear up your confusion on the right side? If not, we can go over it again. Okay. Yes, no? Maybe? I can go over it again. I mean, we got time. We got loads of time. Okay, cool. Wonderful, wonderful, wonderful. Yes, just it has to be to the left of the right pointer and to the right of a left pointer. So yeah, just imagine there's a null pointer right there. Bum, bum. Okay, as you can see, here's an answer. I actually made a mistake here. This should be 1, 3, 4, 6. Oh, I didn't even write the 3. Oh, let's just fix that right now. Dun, dun, dun. There you go. 1, 3, 4, 6. Oh, 1, 3, 4, 6, 7, 8, 10, 13, 14. Okay. So now we get to do post order. And we can go ahead and do that. So first we're gonna go down. We notice the dots are to the right. Gonna go down. We're gonna hit that 1. I'm gonna hit that 4, then 7, then 6, then 3. And then go all the way down. Then 13, 14, 10, and 8. And that is indeed the answer. Yes. 1, 4, 7, 6, 3, 13, 14, 10, 8. Oh, another cool thing about the in order, if you have like a actually binary search tree, notice how in order actually prints them out in order. This is unique in binary search trees versus binary trees. Binary trees simply means that it has two, like you have at most 2 children, while binary search tree has the added requirement that, like Catherine was explaining, that to the left side, it has to be values only that's less than, and to the right side, it has to be values that's greater than. But since this is a binary search tree, then in that case, it does come out in order. Dun, dun, dun. I think that's all. Oh, yes, that is all. Any questions, comments, concerns, heresies? Anything? We finished like 23 minutes early, so I mean, the floor is yours if anyone's confused about anything. Yes, I can indeed do post order again. Thank you for asking. Wonderful. Oh, yes. Okay. I'll try to go over it very slowly this time. Actually, you know what? We'll do it together. This is what we'll do. We'll do post order first. Okay, we're just gonna delete this. Wonderful. Okay. So this will be a more interactive way. Can anyone tell me, as we follow this line, which node is hit first for post order? In the comments or in the chat. Yes. Which node are we gonna hit first? Wonderful. Yes. Oh, yes. 1. Next, which node, as we follow this blue line, which node are we gonna hit next? After we've hit 1, what's the next pink dot that's being hit? Wonderful. Yes. A master's. Okay, and the next one. After 4, we keep on following this blue line. And we're gonna hit yes. Look at the audience participation. You guys are geniuses. Okay, after 7, we're gonna hit which one? Dun, 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 dun. After 7, which one do we hit? This is post order. What's the next pink dot? You guys got this. I believe in y'all. Yes, 6. Wonderful. Oh, why we don't go to 13? Oh, that's probably my bad on how I interacted. Okay, it just overlaps a bit. Don't mind me. How we draw this blue. So are you confused on the placement of the blue line? It's kind of, you just give it a like weird fancy border. Okay, so like in here, you just give it like a fancy border, so to speak. The reason you need to go to 13 next is because if we follow this blue line, oh wait, no, I am right. Okay, if you follow this, you have to give this whole thing a border. You also have to like basically reach this 8. So the reason you don't go to 13 is because you don't want to, it's not about it being a circle. Because if you make this like a circle, wait, let's see if we can shape. Yes. If we basically, oh my, here, I got this. There you go. If we make this a circle like this, when is 8 ever gonna get hit if it's in order? You know what I mean? When is 3 gonna get hit? There. Yes. Oh. Yeah, if we make this circle thing, you don't get to hit, like basically 6 will never get hit. So let me actually make this a bit tighter. So let's draw it the wrong way. So what you're being confused about is like right here. Do you see how this would be a problem? Just making this really tight border. 6 never gets touched, and that's bad. So in end, this is how the way we're gonna actually draw this is we're gonna really tightly follow this node path. Oh, I got this. So we're gonna hit this 3, then this 1, and then we're basically gonna curve inside, and then we're gonna curve out again, and then we're gonna curve inside, and then curve out again, and then we're gonna curve inside. So it's like we only evaluate one side of the tree at a time. Yes, we only ever evaluate one side of the tree at a time. So in the end, this is what happens, this curve. Yes, we only ever evaluate. And after you've made your little squiggle, here, I'll make it a different color. Dun, 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 dun. Okay. After we make this little squiggle, let's just go over, let's do post order. Basically, you're just gonna add like a dot on each side. So here's, oh my, this is terrible. Here, circle. So each time we're just gonna imagine, as you go, like, let's say pre-order, we're gonna add a dot to the left, 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 to the left. You can draw them out. Another technique I've seen is just to make things extra clear. Some people just put all 3 dots at once, and then it's like really clear on then which one goes first. This will also solve the problem of where to put, this will also solve the problem of when you're confused on where to put in order. You can just put all 3 dots and it'll basically fix itself. Wait, hold up. We going. Dun, dun, dun. Dun, dun, dun. Oh my goodness. I am a master drawer. Oh yeah. Okay, these dots might get a bit confusing. So you just gotta go with whatever is easier. If like the other method was easier, that's totally fine. I just find I'm like kind of a visual person, so this is easier for me to just quickly be able to do this. Because on the test, you will be asked to like basically print out things in order, or post order, or here we go. Basically in order, post order, and pre-order. So we just go quick. Okay. Actually, this might have made things more confusing. But basically, you're just gonna hit, oh, we hit this left side, so we print out 8. We hit this left side, print out 3. Hit this 1, print out 1. Hit the 6, 4, 7. Notice how none of these have left dots to hit, so then we're gonna hit 10, 14, 13, and so on and so forth. You would do this similarly. Let's do in order next. Oh wait, we were confused about post order. Let's do post order next. So now it becomes very clear on which nodes you hit next. So post order on 1, you hit 1, delete that one. Then you print out 4, since that's the next one you hit. Then 7, then 6, then 3. And then we go to 13 because now we've established that this is the path we need to follow. And we have to delete like the right dot, so to speak. And then we delete this 14 dot, then 10, then 8. And now we're only left with in order. And we can go on and so forth. Does this make sense to everyone? Is everyone clear now? If not, I can go over it again. We got 15 minutes left. Yes, we can do an order. Okay. We'll do this interactively as well. Dun, dun, dun. Okay. We're at in order. Anna, does it make sense where the dots are placed? Yes, no? Okay. So we can just go over the thingy then. Okay. So what's the first dot that's hit? This is public for anyone who wants to go for it. What's the first dot that's hit in order? Which one's hit first? 1. Yes. What amazing geniuses. Okay, we hit 1. Next, what's the next dot we're gonna hit? It might get a bit tricky here because of the diagram. It can look a bit confusing. Yes, 3. Because notice, although I didn't draw these overlapping, like technically this should be overlapping. I mean, technically, this should be all the way here. That's more accurate. Okay. Because remember, we're doing like a little fancy border thing around. Okay, next, after 3, this dot is hit. What's the next dot that's hit? Wonderful. And then 4, we're continuing on a path. 6, yes, you got it. And then, yeah, oh my goodness. Yes, wonderful. And then, which one's next? Yes. Which one's hit next? Do, 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 do. Wonderful, amazing. And then final 2. Let's see. Actually, here's the tricky part. I can see where the confusion arose. It's actually 13, 14. When we are following this path, notice how we're trying to hit this one, but we're on the left side. Okay, we're kind of being blocked by this arrow right here. We can't like basically reach over. It's not its turn yet. So first we hit 13, then 14. You can imagine this. Here I can make it clear. Like it's kind of like hitting like this. You can't reach over with your thing and like hit it like that. You're basically, do you see how that breaks the border? Okay, yes. So it might be beneficial to draw like a tighter border than I have, like really tight. But just recall that you basically can't overlap over because that breaks the border. Yes, wonderful. Learning was done today. So is everyone good now? We can go over another example of another tree if you want. Oh, where to place the dots? Basically the dots, there's like left side, bottom, and right. And I think what's what can be rather beneficial for y'all is if you just basically draw them all out. So if you just all at once go for it, and then you can delete it. So basically just imagine in your mind, where would the left one go? I don't know, is there a pen tool? No, there's not a pen tool. Okay, Scrabble it is. Okay, so where this left one would go. I hate this. Is there paint still? Yes, wonderful. Dun, dun, dun. Okay. Oh, can everyone see my paint or not? Wait, it's not copy and pasting. Please. Copy. Paste. Dun, dun, dun. Oh my. Oh. I meant like how to remember which dot goes with each order. Oh, which dot goes with the order? Yes, I can explain that to you. So pre-order, basically notice how in pre-order, let's see, pre-order, it makes sense because just think of it as like going like counterclockwise, and just logically speaking, pre-order, it means that like that node is hit like the very first shot. Like because of pre-order, if we go back to our code here, notice how the first thing it does is print it. So when you're looking at your tree, you can think about like, oh, this 8 should be printed like the very first thing in our path. Our path should basically say, if we understand pre-order, where pre-order means that you have to like execute your command before you continue on. Like the first thing you do is execute command. Then you know that when you're on this path, you're basically gonna hit the left first. You're gonna like, because when you visit this 8, it better be printing out. So similarly here, we can just know that when you hit this 8, it better be printing out. So that's pre-order. In order, and then after that, you just like basically you're like, oh, if this is pre-order, in order must be in the center. And then post order must go to the right because it's going to be the last thing it does. So you can kind of think of it like in terms of the root node. So pre-order, it means that the root node, like the very first thing that should be printed out is the root node, because it's the first node you visit. So it has to print out immediately. And post order, because it says post, you can imagine it saying the root should be the last thing that hits. So it should be at the very end. And then in order is just like whatever is left. Does that make sense? Is that helpful at all? Okay, perfect. And Catherine, I don't know if you want to go over deleting a node again.
Yeah, I can do that.
Here.
Yeah, let me just.
Do you want to share your screen, or shall I, or?
Either way works. I'm probably not going to move from that side though.
Okay.
So it should be fine.
Oh, wait.
Yeah. So erasing, the important thing to remember is for 2 children, for leaf, you're just deleting the node. If it's only got 1 child, you're just replacing it with its child. But 2 children is where it gets a little tricky. So you're going to be essentially traversing down from the node that you want to delete to find the successor node. And so you're going to be finding essentially the leaf that you want to replace it with. So in the top example, you're going to be going down until you find 60, which is the next one you want to find, which is the next one in terms of keys. So then you would swap the 2, and then you would delete what was originally the leaf, but is now the node that you want to delete. So the top example, you end up finding 60, and you're switching 50 and 60, so you delete 50 as if it were a leaf erase. So in the bottom example, we have 6, so you find 7, which is the next one that you're going to want. And so in terms of keys, and so you're going to swap them and then do essentially deleting a leaf node again, because you have essentially put the node that you want to delete into the position where it is a leaf, and therefore you don't have to do anything extra to delete it. Are there any particular questions about that, or anything you would like me to expand upon? Just let me know. I know it's not the most intuitive. Essentially, yes. Yeah, you're swapping the information of the two nodes. Sometimes there's more than just a key. That's a bit more advanced, but you're just generally switching the information and then deleting the leaf that has the former key and information that you're trying to delete. Anything else? A PA4 question. Sure. I know that I need to leave in 4 minutes to attend a different review. Sophia, I don't know if you have something you need to attend to at 3.
Okay, I can see. We can stay a bit. Like we'll see. Okay, what's your question? Yeah, go for it. I hope I know how to answer this. If not, that'll be kind of awkward. What's the question? Go.
I still have 4 minutes in case.
Yeah. Traversal. How do we get back up to the tree?
Oh.
You mean from the slide? Or oh wait, I just finished. No.
In terms of traversal, it's largely going to be recursive. So that's probably, I think that's what you're asking, kind of. So once it reaches that bottom situation and it doesn't find what it's looking for.
Can you specify what slide we're talking about?
Yeah.
Oh, wait.
That would probably help as well.
Is there one that is the one without code? Oh, like this one?
Oh yeah.
Oh, how do we get to, like, how do we go back to the bottom? Okay, this kind of goes on with basically the stack of the function. So you print out 8, correct? And then your code tells you to go to the left. Now this basically puts the node 8 function at a halt. Imagine if you have a function just like, say, sum 2 numbers. Do you agree with me that, like, if you go to, like, let's say instead of pre-order print, it was like there is another function here that was kind of like, oh, this is gonna be wonderful. That's gonna be like sum 1, 2. It would, your whole code would just basically stop and calculate the sum of 1, 2, return the result, and only then will it continue on. Correct? Can we agree on that? Yes, no? Okay, perfect. So with that in mind, what's gonna happen here is, like, you're gonna pre-order print. Everything is put on a standstill until this returns. So we're gonna go on this 8, and now we're at 3, right? So now we're completely, we're at 1. We print out 3. Again, the same thing happens. We hit this line and we're gonna go left. Everything gets on a standstill where we go to our 1. On this 1, we're gonna check now. We print out the note. We're gonna go to our left, so we're gonna go to left. What's to the left? On our left, there is a null pointer. So all this code is basically gonna get skipped. And the null pointer code is done. So what this means is, since the null pointer code has finished executing, you can basically stop the number 1. You can basically stop the null pointer and go back to this 1, because now you were stuck here. Now this code has finished, like pre-order print null pointer has finished. So now you get to go to the right. Yes? So you go to the right and notice how there's like a null pointer there. And once more, it skips this whole code. So you're finished with that part. You go back to the 1. You notice how the 1, it has finished executing. The pre-order print to the right is like completed. So now we basically pop back again and we go back. Oh wait, here we go. Yeah, we were at a 1 and we go to a 3. Once more, notice how our 3 was stuck at this line, but it can now continue on because 1 and like everything to its left has finished executing. So now we're at 3. Did you see how we were able to pop back? It was because the reason we were able to pop back was because everything was left at a standstill, but it wasn't completed. So everything was put on hold until it was to the left. But the memory still has it like in order, like that you still have to finish this function. So that's how we were able to pop back, basically. Does this kind of make sense, Oma? In the how we're able to pop back? If not, I can keep explaining. How it doesn't reprint everything? Okay, yes, perfect. So let's just continue walking through this example. So we're at 3, yes. We're at 3. We have finished this line right here. We're done with it. So now we're gonna go everything and print everything to our right. Okay, what's to our right? Our 6. So now we're calling basically node 6. We're pre-order printing 6. And once more, our 6 starts like from the top. It's not a null pointer. It prints out 6. And it's going to look to its left. To its left, there is a 4. So same thing. It's not a null pointer. It's going to print out 4. And it's going to look to the left. Our 4, there's nothing to its left. Oh, well, first, node left. This will basically be null pointer now because there's nothing to the left. It is a null pointer, so it just skips this whole thing. So now our 4 is basically finished with this command. This is now our pre-order print node 4. It's done looking to the left. So now it gets to look to the right. Once more, there is nothing there. Nothing is like at the right of our 4, so it basically finished executing this block of code because there's nothing to execute. And we go back to our 4. Our 4 has finished executing this last line. And now it has finished, now that 4 has finished executing. Notice it did not print out again because there is not another cout statement here. Like this is not there. It just finished. It doesn't print out again because it's just done. So now it gets to go. You pop back to our 6, and we're going to do this exact same thing, but to the right. Our 6 was at this line. It has finished evaluating that line. So now it goes to the 7. And the same thing happens with the 7. It's going to print. It's going to go left. There's nothing left, so that finishes. It's going to go right. There's nothing right, so that finishes. And it's done. The 7 has finished. Now we're at our 6 again. It has finished looking at our right, which was our node 7. That has finished executing. So then this one's done. And with the 6 being done, our 3 is now also done. Because our node 6, it was stuck at this line, but now that has finished executing. So it goes back to 8. Does that make more sense, Oma? Yes, perfect. So that's kind of how it doesn't print out again, is because we only have one cout statement. It's kind of a tricky thing to wrap your head around, but if you do a few more examples on your own, you'll be able to see how none of these are going to be repeating, because we're basically telling it print, go left, print, go right. But once it finishes going to the left, we're not going to print it out again. Okay, and someone had a question on the code. When is that one of the instances when you use the compare and deleting the nodes? It might be actually. Let's see. Erasing the nodes. You know, I'm not quite sure. Abdur, I'm sorry if I just butchered your name. That is that is on me. I'm not quite sure when you use the compare and deleting the nodes, but if you send me an email today, I will respond to you. With your question, just email me the question with a bit more specifics on the email, and I'll be sure to get back to you. You good? Okay, cool. So with that, we are done. Thank you for coming by. Yes. Goodbye.